I'm Ryan. I'm a science teacher.
I'm Cheryl, and I slept through science.
Each episode will tackle a science question you may have learned in school, but can't quite remember or fully explain.
And I'll take the risk of asking the dumb questions so that we can all understand the science we slept through.
The bell has rung. Let's get started. Welcome to lesson 32. We are in our color unit. Cheryl, do you have another colorful question?
I do, and actually this was inspired by myself.
Ooh, you inspired yourself.
Like I do. I was listening back to our podcast.
Okay.
And because sometimes I do that, actually.
You're just reviewing your notes, right?
Yes.
Reviewing for
exactly.
The test.
Mm-hmm. Yeah, for the big test. Mm-hmm. And in a previous lesson on color, where we talked about the colors of the rainbow, I asked you some follow-up questions that kind of were brought up.
Is that the one that you asked me a bunch of follow-up questions?
Yes. And one of them I asked that as we've continued to talk about color, I'm still like, gosh, I just can't explain this yet.
Okay.
Is I asked, what makes my red shirt red?
Okay.
Or in this case, your red shirt, because I guess I'm not, or my red curtains.
Yep. Okay.
But like, okay, I get light is bouncing off and there's the wavelengths, and then you're like seeing one color of wavelength that's like reflecting off of different things. But what actually makes it red? Like, what about whatever, like the dye, the red dye, what about that makes it red? So that's my question.
So you're asking what makes, in this case, my red shirt red, but on a deep level.
Yes.
Okay. You've already talked about a couple of things. You talked about light bouncing off. You mentioned something about wavelengths.
Yep.
How do you think all of that is related?
Well, I know that the different colors are different wavelengths of light.
Okay.
And so when I look at your red shirt, it is absorbing all the wavelengths but the red one, and then bouncing the red one back to me. And that is why I see red. I'm pretty sure that's because you did explain that part. I'm pretty sure that's how it goes, or it's the complete opposite, but I'm pretty sure that's the way it goes.
Okay.
Why? What about it? Okay, I know that like somebody made your red shirt and they dyed it red. So, okay, fine. They used red dye. But like, what about it, that dye absorbs some wavelengths of light and bounces off one?
Any ideas as the answer to that?
Well, I mean, okay, because we talked about how like different like minerals or different things like have different properties. So then I'm assuming that, and I'm sure a lot of dyes these days are synthetic. So then they're like maybe like mimicking those properties or something, but still like, what are those properties that would make something absorb certain things? I know with the sky being blue, it actually had to do with the wavelengths being shorter and actually like the length of it interacting with the gas. But like I could buy dye in any color and it would make things different colors. So is there something different? Well, obviously there's something different in that dye, but what I don't even know what my guess would be as far as like, what about it makes it different?
Yeah. No, I think actually what you've described makes sense. First of all, it helps me know what you remember from previous lessons, which is useful to know what we can build off of. And then also understanding where your question actually lies. Because you can ask that question, why is my shirt red? at multiple levels of depth. And so
Yeah.
you describing the pieces you know, and up until the point where you don't know, that really helps me know where is it that we need to kind of dive in and get some more clarification and more detail around.
Great.
To answer your question, I'm going to start by doing a little bit of review of some of the things you already described to try and also put a visual to some of it. And there may be some other little questions that come up in the process, but it'll give us a foundation that we can then talk about to then build the pieces that you don't have. Does that work?
Yes. Love that.
So I'm going to do some drawing here.
Ooh, are you going to share your screen?
I'm going to share my screen and I'm going to draw some things.
That's great. Well, that's a good opportunity for me to remind our listeners of our podcast that they can also check out our YouTube, where they can see Ryan's amazing drawings.
Oh, because clearly I should have been an artist. What am I doing being a science teacher?
Yes. Oh, yeah. This is the moment where we see that.
Let's start with the circumstance that you described. We're going to zoom in onto a molecular scale. If we're looking at the surface of a thing, like, let's say, my red shirt. Okay. And the surface of that, and we'll just start by kind of just drawing a line to be the surface. I should probably have drawn it red, huh?
Yes.
Since it's a red shirt. And we'll say red shirt. Because I'm being good and I'm labeling my diagrams.
Yeah, that's part of science, right? Labeling.
It's definitely part of science.
Great.
And then, like you said, the light comes and in most circumstances, let's say we're outside, where's the light probably coming from?
The sun.
The sun. And what colors would we have represented coming from the sun?
Sunshines are yellow. Oh, but the colors are all the colors.
All the colors of
the rainbow.
The rainbow, which we've talked about. Do you remember what those colors are?
Red, orange, yellow, green, blue, purple.
Perfect. Wonderful. And we can hear more about that song on an earlier lesson if people want to go back and listen to that. And do you remember, because you've already referenced this before, about wavelengths and how wavelengths are connected to color?
Yes. Different colors are different wavelengths of light.
Yes. And the redder colors
are longer.
Nice job.
Okay. My mnemonic device worked.
Why don't you just remind everybody what your mnemonic is?
Okay. I don't know if this makes sense to anybody else, but it helped me remember just now that warmer colors are longer because if you keep something in the sun for longer, it gets warmer. I think I said that a little more succinctly this time. So hopefully that's actually is helpful.
Yes. And remember, that may or may not be 100% accurate, but it helps you remember. So that's okay.
Yes.
Okay. So do you see what I'm doing here? Do you want to describe what I'm doing?
So Ryan is drawing a very squiggly rainbow with arrows on the end of each of the colors of the rainbow, showing that this is sunlight and all the colors of the rainbow in the sunlight that are pointing at the red shirt. And each squiggle is tighter and tighter as he gets to the cool colors. Shorter lengths of waves.
Shorter and shorter wavelengths. Exactly. So obviously, if I was really good, I would be measuring the exact wavelengths and all of those things, because there are very specific wavelengths that equate to each color.
And then we'd be here all day.
And we'd be here all day. Yeah. Just for reference, since I know you cared a ton, the reds are usually around 700 nanometers.
Okay.
And a nanometer is 1 billionth of a meter.
Holy moly.
Okay. And then the purples are around 400 nanometers.
Okay.
And then that's the visible spectrum. That's the range that our eyes can see. And I say around because it's not exactly, and and then everything in between. But just so those are those different wavelengths, but they're all streaming from, I should probably have drawn the sun, huh?
Yeah.
And look, I made it yellow.
Yay.
Because it looks yellow to us,
yes.
Even though it's white. So we've got all of those wavelengths coming from the sun, and they're all bouncing onto the surface of my shirt.
Mm-hmm.
And I guess there's no sunlight in here. It's all artificial light for right now, but same sort of thing. It's all made to look like sunlight. It still is mostly the colors of the rainbow.
Yep.
Good so far?
Yes.
Okay. And then you talked about how some of those colors bounce off and others do not.
Yes.
Right?
Did I get it right?
Well, why don't you just remind us real quickly, what did you guess?
I would guess that orange, yellow, green, blue, purple get absorbed and the red bounces off. And that's why we see red.
Okay. You are correct.
Yes, I remembered correctly.
Yep. So the red bounces off. And technically, this is not pure red. So it's not just going to be red, right? There could actually be some green and a few of these other wavelengths that are in there. But to simplify and make sure that we're getting it, yes, we're going to say the red bounces off. And we know that that matters because, and now this is not for me to scale at all, but like.
Are you going to draw an eye?
I'm trying to.
Oh, good. There are lashes on the eye.
Sort of. I know it's weird. It doesn't look very good, but that's how we can actually see it, is because those red wavelengths have to actually enter our eyes. Whereas all the rest of them, all these other ones down here, end up getting absorbed by the material, all of the different pigments and things that make up the red shirt. Good so far?
Yeah.
And this is all basically what you've already described, right? I'm just kind of putting it visually and kind of connecting it all together, but you described this part already.
Yep.
Okay. And your question was, what's going on in this part that I kind of circled there?
Yeah.
Why does the red bounce off, but the other ones get absorbed?
Yeah.
There's sort of a two-part answer to your question. The first part is something that I don't think I've mentioned before. And the second part is related to something that I did mention before.
Okay.
First, wavelengths are also connected to an amount of energy.
Ooh.
We've just talked about wavelength and color, and that's true. But in addition to that, the shorter the wavelength, the higher the energy of those light waves.
Interesting.
And a way to think about it, it's not necessarily 100% accurate, but close enough. A way to think about it is if, let's say, we were to take that red wavelength, right, that's really long, and you were to just squish it, you take that same amount of energy that took up this amount of space, I don't know, like a foot, and if I squish it down to now it's taking up an inch, I took that same amount of energy and it's in a smaller space.
Like a coil.
Kind of like a coil. But then all light is still traveling at the same speed, which means whether it's these long wavelengths or these short wavelengths, you're actually going to get more of that light energy in the same amount of time if it's more scrunched together.
Kind of like a twisty, windy road.
Yes, you've got, because you're actually driving a longer distance.
Yes.
But even though if you have point A and point B, a straight line is going to be a shorter distance.
Yeah.
Right. And you're still, point A and point B aren't moving. But if you're getting a windy road, then it takes longer to get there. Yes, that's a good analogy. Is this making sense so far?
Yeah.
Okay. So in addition to it being a longer wavelength, it's also lower energy.
Okay.
And vice versa, with the more blue end of the spectrum, that's a higher energy.
Got it.
And just as a side note, this is one of the reasons why ultraviolet light, which is the light that is beyond the violet, beyond the purple that we can see, can cause a sunburn.
Are you serious?
Mm-hmm. Is because it's higher energy than the visible part of the spectrum.
Whoa, really?
Mm-hmm. And as you continue to go, and we haven't really talked about this, we haven't really talked about the colors we can't see, but after ultraviolet, you end up with, there's other wavelengths as well that you've heard of before, like X-rays.
Yeah.
And gamma rays, which you may or may not have heard of, but gamma rays are nuclear radiation. Those are the ones that in all the comic book things, you get hit with gamma rays and then you have this mutation and then you have superpowers.
Yeah.
Which is not true. It's actually, you get hit with gamma rays and you die. I mean, maybe not immediately, and depending on how much and how long your exposure is, it's not a guarantee, but that's the deadly type of radiation.
And that's just like shorter and shorter wavelengths.
And shorter wavelengths. Yep.
It gets to be a dangerous amount of energy.
Yep, exactly. Mm-hmm. And it's also because it's shorter. In that case, it's also dangerous because now the wavelength ends up being like the size of a DNA molecule, for example, which means it can actually break apart DNA molecules.
What?
Which is bad. Yeah, it's bad.
Wow.
Yes.
I thought those were all totally different things. I didn't know they had something in common.
Yeah, it's all light. It's called the electromagnetic spectrum. You may have heard that before.
Yeah.
And the visible part of the spectrum is a really, really small portion of that. Most of the electromagnetic spectrum is light we can't see. On the opposite side, microwaves are light. Microwaves aren't just like the microwave ovens, but like microwaves are actually waves. They're bigger.
Microscopic waves.
It's more like micro scale, not necessarily microscopic, but yes. Okay. And then radio waves. You've heard of radio waves?
Yeah.
Like AM, FM radio.
What?
Yeah, that's light.
So you could say like, oh, what does the radio and nuclear things have
Radiation.
in common?
Yeah, they're all light.
All light rays.
Just to give you an idea how big, remember we talked about like a DNA molecule on the small side.
Yeah.
Radio waves, some radio waves can be like a mile or more long in one wavelength.
But we can't see it because
we can't see it.
Wow.
Yeah. So that's all light. We've focused on the visible part of light. Maybe at some future time, you're going to have a million questions about the light we can't see, but
yeah.
So anyway, back to the red shirt. So because the different wavelengths of light have different amounts of energy, the molecules can absorb only certain energies of light. And that has to do with these things called electrons. And this is the second part that I mentioned that I said I sort of referenced previously in our glow in the dark episode, when we talked about glow in the dark paint with Beth.
Yeah.
I talked about and kind of glossed over how the electrons absorb some energy and then re-emit it. Does that vaguely sound familiar?
Yeah.
Right.
Yeah.
And that re-emitting, and I said, normally they do it really quickly, but with glow in the dark paint, they absorb it and then slowly emit it over time.
Yes.
Right. Well, that's absorption and re-emittance is happening all the time. And that's part of what's happening here. But they can only absorb some wavelengths. And that is based on the structure of the atoms and the molecules and where their electrons are. And so depending on the size and shape of those atoms and molecules, some wavelengths of light can be absorbed and others can't be. And so some end up getting absorbed into your whatever the substance is, like in this case, my shirt, while others can't be absorbed. And so they end up bouncing around and those wavelengths get bounced back to our eyes. Another way you can think about this, and you did sort of talk about this a little bit in your mnemonic, right? If I was wearing a black shirt heats up more in the sun than a white shirt.
Yeah.
Because it's absorbing almost all of the wavelengths of light. Whereas a white shirt is reflecting almost all of the wavelengths of light. So it's absorbing less energy, and that energy ends up making the molecules move faster, way back to a long time ago, our hot and cold unit, right? And the molecules moving faster is a higher temperature. That's how we perceive that.
That's so cool. So, because I knew that because when we talked about penguins, I told you how penguins
Yes.
turn their back on the sun if they're cold.
Because they're black on the back.
Yeah. Or their belly, they face the sun if they're warmer. Yeah.
And that'll do more reflecting because it is actually literally absorbing some of that light energy from the sun if it's a darker color, and it's reflecting more of it away if it's a lighter color. Now, there's no perfect black or perfect white, although there are some artists who've worked on substances to try and be like the blackest black and the whitest white. And that's a whole nother thing that's really cool and interesting, but we don't have time. If you want to look up something interesting, you can look up something called Vanta black, V-A-N-T-A. Look at some videos on YouTube. It's pretty cool and freaky. But even like the chair behind me that I'm sitting in is black. Right? But you can still see light coming off of it. It doesn't completely disappear because it's not perfectly black. It still is reflecting some wavelengths of light.
Yeah.
But it's absorbing a whole lot more than, say, the wall behind me or the white part of the Star Wars poster behind me. That's doing a whole lot more reflecting than it is absorbing.
That's so cool. Wow.
Any other follow-up questions with that?
So then if somebody is like making a synthetic dye, they're just putting in the electrons that reflect red into the red dye. It's
not the electrons themselves, it's the electrons in the atoms that are in molecules. So it's all of them and yes, the electrons are doing the absorbing and stuff, but electrons by themselves are all exactly the same. Their positions and where they are in a molecule or an atom is what is different. And as you change the atoms or you change which atoms are interacting with each other, that's what changes whether the electrons can absorb or not absorb and re-emit and how that works. And again, it's more complicated and I could get into it if you really want to, but.
No, I think that's good for today. I have a lot more things I'll write down for future lessons now.
Good plan. And now it's time for your quiz, Cheryl.
Oh, I actually have a note that I have an appointment I need to get to. So I'm gonna go, but like
I need to see that note, please.
Oh, I mean, I do have it, but similar to some of those light rays, you can't see it. But
well, you know what? As soon as your parent comes to pick you up, they'll call down to the office or they'll send a pass for you. So why don't you stay here and see if you can get as far as you can through the quiz. And then when it's time to go, it'll be time to go.
Oh boy, that gave me that stomach feeling like when I was in school.
Oh, you're welcome.
Yikes.
Okay, first question. Describe the relationship between wavelength, color, and energy for light.
Different colors are different wavelengths.
Okay.
Different lengths have different amounts of energy, and the shorter ones are more energy because they're covering more distance in the same time as the longer wavelengths, which are a little bit of a straighter line.
Yes.
And so
the distance piece is technically more of an analogy than what's actually happening, but it gets you to the right place.
Okay.
Because light's funny, it's a particle, but it is also a wave, and so it's not exactly traveling like this, like in a wave shape, but it sort of is. It's complicated.
Interesting.
Yeah.
Okay.
Yeah. And the color piece?
Different colors are different wavelengths, and there's only a certain range of wavelengths that we can see.
Yes.
And those are the colors of the
And
rainbow.
what's the relationship between wavelength and color?
The longer the warmer, and the shorter, the cooler.
Great. Wonderful. Next question. Why can ultraviolet light give us a sunburn, but the colors of the rainbow can't?
There's more energy in ultraviolet light.
Yep. It's higher energy. Nice job.
Yay.
Okay. Why do dark colored objects tend to heat up faster than light colored objects?
Because it's absorbing all the colors. So it's absorbing energy, which makes heat.
Whereas the white
Bounces it all. It's reflecting all of the colors. And so, I mean, it's still going to get hot eventually, but like not in the same way.
Yeah, wonderful. Okay, last question. What, and I'm going to use the word property because that's the word that you used earlier, of an object allows it to absorb some colors while reflecting others?
The electron.
Oh, can you tell me a little bit more about that?
Well, the electrons are all the same, but apparently their position within the atom, the molecule,
Either.
okay, causes them to reflect different wavelengths and absorb different wavelengths.
Yes. Wonderful. A plus. Nice job.
Yay!
And I can tell you were a little unsure about that last one.
Yes.
But you did a great job.
Awesome.
See, you're becoming a color queen.
Ooh, that's so fancy.
It is fancy. And so we will end on a fancy note then, because we're just about out of time. So why don't you pack up your stuff and get ready for my closing remarks. You can follow us on Instagram and Facebook at I Slept Through Science, or on Twitter at Slept Science.
If you have dumb science questions like I do, please send them to us. You can email us at isleptthroughscience@gmail.com, or you can even send us a voice memo and we'll play it on the podcast.
Please rate and review our podcast to tell other people what you think about it, subscribe to make sure you don't miss an episode, and share about our podcast on social media.
Thank you to Beth Reed Miller for the artwork. You can check out more of Beth's artwork at Beth Is Something. Okay, great. Thanks. Bye.
The bell doesn't dismiss you. I dismiss you.